Discuss today the chapter 13 of our part 2 NCERT book, Nuclei. As you have already studied from chapter atoms, according to Rutherford, the entire mass of the nucleus is concentrated in a small region known as the nucleus. And he also stated that the nucleus is positively charged with a charge equal to Za. How will you represent a nucleus? A nucleus is represented by Zxa, where Z is the atomic number or the proton number. A, it is the mass number. Constituents of nucleons. Since the nucleus is positively charged, the nucleus has the positively charged protons. This power off. After the discovery of neutrons by James Chadwick, Heisenberg put forward the proton-neutron theory. Proton-neutron theory. So, the nucleus has two constituents, protons, which makes the nucleus positively charged, and neutrons. So, the mass of protons and neutrons will form the entire mass of the nucleus. Entire mass of the nucleus. A nucleus is represented by Zxa. Z is the atomic number or proton number. A is the mass number. Mass number A is equal to number of protons plus number of neutrons. So number of neutrons N is equal to A minus Z. Number of neutrons is A minus Z. So this Z atomic number, A mass number, the entire mass is concentrated in the nucleus. How to represent the mass of a nucleus? To represent the mass of a nucleus. Since the size of the nucleus is extremely small, the mass of the nucleus is concentrated in a very small region. For representing the mass, we are using a unified atomic mass unit represented as U. Unified atomic mass unit. Unified atomic mass unit is 1 by 12th mass of a carbon 12 atom. One atomic unit is 1 by 12th mass of a carbon 12 atom. That is 1 by 12th mass of a carbon 12 atom is 12 gram by Avogadro number 6.23 into 10 raised to 23. Changing gram to kilogram and multiplying by 10 raised to minus 3, we will get this value as 1.66 into 10 to the power of minus 27 kilogram. So 1 atomic mass unit is equal to 1.66 into 10 raised to minus 27 kilogram. This unified atomic mass unit is used for representing the mass of nucleons. When I say nucleons, this is a term collectively to neutrons and protons. The constituents inside the nucleus are known as nucleons. So if you want to represent the mass of proton, mass of neutron, we can represent the mass in atomic mass unit. Okay? If we use Einstein's mass energy relation, E equal to mc square or delta mc square, the energy corresponding to one atomic mass unit is 1.66 into 10 to the power of minus 27 into 3 into 10 to the power of 8 the whole square, nearly equal to 931.5 MeV. Okay, see this energy we are getting in joules. We can divide that with the charge of electron 1.6 into 10 raised to minus 19 coulomb, and converting into MeV we are dividing with 10 raised to 6. So you will get the value equal to 931.5 MeV. One atomic mass unit is nearly equal to 931.5 MeV. Okay. Now, around 1,500 nuclei are known to us. 1,500 nuclei. Out of that, 1/5 of the nuclei are stable, but the others are unstable. Since the nuclei are unstable, you can say that the nucleus is existing in a form known as isotopes. Isotopes are atoms of same element having different mass number. Same element having different mass number. Same element having same proton number, different neutron number. Example, 1H1, 1H2 and 1H3 are the isotopes of hydrogen. They are existing in the weighted average in the universe. 1H1, protium or hydrogen. Atomic number 1, mass number 1, so it has only one proton. 1H2, very heavy hydrogen, it has one proton and one neutron. This is tritium, one proton and two neutrons. Also, atoms exist as isobars. Nuclei exist as isobars. These are atoms of different element having different element means their atomic number will be different. Having same mass number. Same mass number. For example, 1H3 isotope of hydrogen, 2He3 isotope of helium. These are isobars. Isotopes, isobars. Now, take the case of 1H3 and 2He4. In this tritium nucleus, there are two neutrons. In the helium nucleus also, there are two neutrons. Atoms of elements having same number of neutrons. These are known as isotopes. Isotopes, isobars, isotopes. Atoms of same element having different mass number, so they will have same chemical property. Atoms of different element having same mass number, they have different chemical property. Atoms of different element having same neutron number, they are known as isotopes. For representing mass of neutrons, we are using the unified atomic mass unit. Then what about the size of nucleus? Size of nucleus. Let us consider two atoms. One is helium. Another atom is uranium. In that helium is represented as 2He4. So in helium nucleus there are two protons and two neutrons. Uranium 92, U235 or 238. If it is 92 uranium 235, there are 92 protons are there, 143 neutrons are there. Size of the nucleus, uranium nucleus is big. Size of helium, it has to occupy only two protons and two neutrons, so the size will be small. Okay, we can't say that the shape of the nucleus is not exactly spherical, but on an average we can say that it is spherical. So the volume of a nucleus is proportional to the mass number. As mass number increases, volume also increases. Volume, if the nucleus is taken to be spherical, for assumption 4/3 pi r cube. R is the radius proportional to A. We can say r cube proportional to A. Cube of the radius of the nucleus is proportional to mass number, or r proportional to A raised to 1/3. Radius of the nucleus, are proportional to cube root of mass number. Proportionality sign is replaced by a constant, empirical constant R0 a raised to 1 by 3, where R0 is equal to 1.2 into 10 raised to minus 15 meter or femtometer. 1.2 femtometer. So, the radius of the nucleus R is equal to R0 a raised to 1 by 3. Radius of the nucleus R is equal to R0 a raised to 1 by 3. R0 is a constant, A is the mass number. Suppose we have two nuclei, R1 equal to R0 a1 raised to 1 by 3. Second nucleus R2 equal to R0 a2 raised to 1 by 3. They are differing in their mass number. If we take the ratio, then R1 by R2 is equal to A1 by A2 the whole raised to 1 by 3. You can use this for finding the ratio of the radii of two nuclei. Okay, size of the nucleus. So, we got two important information. One, radius R proportional to A raised to 1 by 3 and volume of a nucleus is proportional to A. If we consider a nucleus to have a volume equal to 4 by 3 pi R cube. Volume equal to 4 by 3 pi R cube. And let us consider a nucleus having average mass of nucleons M. Average mass means weighted average of protons and neutrons in a nucleus. And if that nucleus is having mass number A, this is the total mass of the nucleus. So total mass of the nucleus is equal to MA. The ratio of mass to volume, ratio of mass to volume will be the density of the nucleus. Density of the nucleus is equal to MA, mass of the nucleus. This is average mass of nucleons divided by 4 by 3 pi R cube, R0 cube A. R is equal to R0 a raised to 1 by 3. So if you take R cube, then R0 cube A will cancel, is equal to 3m divided by 4 pi R0 cube. See, the density of nucleus depends on the average mass of nucleons, whether it is a uranium nucleus or a helium nucleus, okay, or a carbon nucleus. The average mass of nucleons is a constant. R0 is an empirical constant, that is also a constant. That means the density of nuclear matter is independent of mass number. Density of nuclear matter is independent of mass number. Helium nucleus or hydrogen nucleus, carbon nucleus, uranium nucleus, all these will have the same density for the nuclear matter. 3m by 4 pi R0, substituting the values, we will get it is 2.99 into 10 raised to 17 kilogram per meter cube. Density is very high. Density is very high because it is of the power of 10 raised to 17. So the density of nuclear matter is very high, the highest density. You may have heard about what is known as neutron star. Neutron stars have only neutrons in their nucleus, that is core. So the density of neutron stars is immense because the density of nucleus of an atom is very high. So if it has only neutrons, the density will be very high. Mass of nucleus is Ma, volume equal to 4 by 3 pi R cube. We are finding the density. Density is equal to mass per nucleus. Inside the nucleus, that is inside that small space of the atom, the protons and the neutrons are embedded. Protons are positively charged, neutrons are neutral charged. how these positively charged neutrons, in spite of the electrostatic force of repulsion embedded in the nucleus. Let us look into that. Let us consider a nucleus. This nucleus is represented as 2He4. The nucleus has 2 protons and 2 neutrons. Nucleus has 2 protons and 2 neutrons. Let us consider Z as the atomic number. Z is equal to 2. Mp is mass of a proton in AMU or in atomic mass unit. This nucleus has A minus Z neutrons. Mass of a neutron is equal to Mn in AMU. If I add the mass of protons and neutrons, I will get Zmp plus A minus Zmn. These 2 protons and 2 neutrons cling together to form the helium nucleus. If I take Mn, capital N, as the nucleus of the helium atom, Mn as the mass of the helium atom, this mass is less than the sum of the masses of its constituent nucleons. Zmp plus A minus Zmn is greater than Mn. That means when the nucleons cling together to form a nucleus, some mass is missing. And that missing mass we can represent it by the letter delta M, and this is known as mass defect. When nucleons cling together to form a nucleus, there will be a mass defect. And this mass defect converted to energy by the relation delta M into C square. That energy is responsible for binding the nucleons inside the nucleus. Hence, this energy is known as binding energy of the nucleons. Binding energy of satellite you have studied in class 11. Binding energy of electrons also you have studied in chapter, that is atoms. Binding energy of nucleons is the external energy we have to supply to dissociate the nucleus into its constituent nucleons. Here, the nucleons are arranging to form the nucleus. So, binding energy is defined as the energy required to dissociate the nucleus into its constituent nucleons. Okay, binding energy is very large, delta M into C square. So, here, instead of this, that is delta M, I am substituting the value. Binding energy is represented by EB, binding energy, is equal to Zmp plus A minus Zmn, number of neutrons, mass of neutron, minus mass of the nucleus multiplied by C square. If I am using instead of this, if I am representing this mass in AMU, then I can directly multiply by 931.5. Here, binding energy is in joules, is in the unit joules. A more important quantity to understand the stability of the nucleus is binding energy per nucleon. We call it as EBN. Binding energy per nucleon is equal to binding energy divided by the mass number. Binding energy per nucleon is a convenient quantity we can represent for, that is, determining the stability of the nucleus, that is Zmp plus A minus Zmn minus Mn into C square divided by A. Okay, if you are representing it in MeV, I am multiplying it by 931.5 MeV. Now I am getting the binding energy in the unit MeV. That binding energy is the binding energy per nucleon. Depending on the value of binding energy per nucleon, we can say whether the atom is or the nucleus is stable or not. For that, let us see a graph. That is the graph showing the variation of binding energy per nucleon. I am taking it as BBN, binding energy per nucleon, and mass number on the x-axis. On the x-axis we are taking mass number, on y-axis we are taking binding energy per nucleon. Here a maximum value of 9 MeV, okay, 8 MeV, like that. Here we are taking the mass number up to 240. The curve is not, a curve is like this. Binding energy per nucleon curve is not a smooth curve. It's not a smooth curve. It has peaks corresponding to elements with mass number 4, that is helium, mass number 12, that is carbon, mass number 16, that is oxygen. So after helium, here lithium will come. After carbon, nitrogen will come. After oxygen, fluorine will come. This binding energy per nucleon has maximum value here and is equal to 8.56 MeV, corresponding to a nucleus Fe56. See, if you refer to this curve, I am drawing it a little more broad. This is the binding energy per nucleon curve. This binding energy per nucleon curve has a broad maximum, and that broad maximum is in the range from mass number 30 to mass number 170. Beyond 170, the binding energy per nucleon decreases to 7.6 MeV. Here, the binding energy is 1.1 MeV for deuterium, helium, carbon, oxygen. Binding energy per nucleon curve is not a sharp curve. Let us see what are the inferences from the graph. First inference, binding energy per nucleon has sharp peaks corresponding to mass number 4, mass number 12 and mass number 16, which shows that these nuclei are more stable than their immediate neighbors. Helium is more stable than lithium, carbon is more stable than nitrogen, oxygen is more stable than fluorine. Binding energy per nucleon has a broad maximum with maximum for Fe. So in this region, the nuclei are found to be more stable compared to other nuclei. The nuclei are found to be more stable. Okay, this stability of the nucleus can be explained. That is, if binding energy per nucleon is high, the nucleus is more stable. Here, after 170, the binding energy per nucleon curve steeps. So here, if we consider the atoms like uranium, they have very less binding energy per nucleon compared to iron. That means here the nucleons have less binding energy per nucleon. Binding energy decreases. Okay, here it shows the nucleus is not that stable. Stability is not there. For lower atom, that is isotopes of hydrogen, the binding energy is less. These are also not stable. Stability is here only. How we can explain the stability? Binding energy per nucleon to 170, it explains the stability of nucleons. This stability or constancy of the nucleons is due to the saturation property of nuclear force that we studied just now. Important two inferences which can obtain from the graph. Binding energy of heavy nucleons like uranium is small. That means, suppose this uranium nucleus we are splitting into two moderate nuclei. the position of this moderate nuclei will come to the broad maximum. That means, by splitting a heavy nucleus into two moderate nuclei, their binding energy per nucleon of the product nuclei increases. Their position will come here. It becomes more stable. Important conclusion, that is, nuclear fission is energetically possible. Nuclear fission is energetically possible because if we split a heavy nucleus whose mass number is greater than 170 or whose binding energy is of the order of 7.6 MeV, we will get two product nuclei and their binding energy per nucleon will come in this, that is step, that is maxima region, so that nuclei becomes stable. Similarly, the binding energy per nucleon of, that is, small isotope cells like hydrogen, deuterium, tritium, these are very small. So if we combine these two nuclei to form a moderate nuclei, their position will come here. That means the process known as nuclear fusion is also energetically possible. These two, that is nuclear fission and nuclear fusion, is energetically possible. That we can explain from this graph. I told you here the constancy of nucleon. For understanding that, let us see the force that is clinging the nucleons together inside the nucleus. If I take a nucleus, that is oxygen, 8 protons are there, 8 neutrons are there. So the 8 protons and 8 neutrons are kept inside the nucleus. Protons are positively charged, neutrons are neutral charged. These protons, 8 protons, will have their own electrostatic force of repulsion, that is the Coulomb force. So these protons will try to exert that electrostatic force of repulsion, but the nucleus is stable. It has the 8 protons and 8 neutrons inside the nucleus. So what keeps the 8 protons, positively charged protons, inside the nucleus is known as the nuclear force. Nuclear force keeps the nucleons inside the nucleus and it is the strongest non-force in nature. Strongest non-force in nature. The force that keeps the nucleons inside the nucleus is the nuclear force. It is the strongest non-force in nature and there are certain properties. Okay, the first property is that, first property of nuclear force, it is charge independent. Charge independent. Charge independent means this nuclear force is independent of whether the charge is positive or neutral particle is there. Charge independent. The second property, it is always attractive. Strongest non-attractive force. Attractive. Charge independent. That means if we have 2 protons, these 2 protons or a proton or a neutron or 2 neutrons, these two, that is proton neutron and neutron will have only attraction. That means this force is very much higher than the electrostatic force of repulsion. There will not be any repulsion. Charge independence, always attractive, that is the strongest non-attractive force in nature. The third property, it is known as a saturation property. If we consider a nucleus, this is a neutron, and this is another nuclear proton. This proton will have its attraction with its immediate neighbors which are coming in the nuclear range. This proton will have attraction with its immediate neighbors which are coming in its nuclear range. So I am using one more property, that is nuclear forces are short range forces. Their attraction is confined to a very small distance. Saturation. This nucleon will have attraction with its immediate neighbor. This proton will have attraction with a proton that is very near. It will not have repulsion, and it will not be attracting with a neutron which is very far. Saturation force. This saturation property and the short range nature of the nuclear force is responsible for the constancy of binding energy per nucleon. Constancy of binding energy per nucleon, that is EBN. Atoms, nuclei whose mass number is between 30 and 170 will have constancy in their binding energy per nucleon is due to the two property, that is saturation and short range force. We have studied electrostatic force, Coulomb force, gravitational force. All these are depending on inverse square law. But nuclear force never depend on inverse square law, and this is not a non-central force. These are the main properties, and that are important. One, the strongest non-attractive force. They are charge independent. They show saturation property, and they are short range force. For representing short range force, now I am using a small graph. That is, let us consider a graph with a distance r and force, nuclear force on y-axis, distance r on x-axis. The graph is like this. I will explain the graph. This corresponds to 0.5 femtometer, and this corresponds to 1 femtometer, and this corresponds to 3 femtometer. So this is 2 femtometer. The distance between pair of nucleons. Nuclear force is attracting up to a distance equal to 0.8 femtometer. If two nucleons are separated by a distance equal to 0.8 femtometer, they will have maximum attraction. If the distance increases, that is greater than 0.8 femtometer, the force of attraction decreases. One more property. If the distance is 0.5 femtometer or less than 0.8 femtometer, the nuclear force of attraction decreases. So on the y-axis, here I am marking it as attraction, and here I am marking it as repulsion. If two nucleons are at a distance less than 0.5 femtometer or equal to 0.5 femtometer, the attraction will be lost and there will be repulsion. So two nucleons cannot come very close to a distance that is 0.5 femtometer or less than that. There will be repulsion. Okay. So here we have maximum force of attraction. Maximum force of attraction means the nuclei will be stable. So that stability, any stable system will have minimum potential energy. Now we can draw a graph with potential energy along y-axis and the distance between pair of nucleons. R is the distance between pair of nucleons. And here we are taking potential energy in MeV. I am taking the value as 100 MeV. This is 100 MeV and this has minus 100 MeV. This is 100 MeV. Now the graph. The graph will be like this. Graph will not meet the x-axis. And this distance here 10 femtometer. This distance corresponds to, it's not in a proper scale, 0.8 femtometer. That's the maximum. Okay, here potential energy is positive. Potential energy is positive means if the nucleons are at a distance less than 0.8 femtometer, their potential energy becomes positive. Positive means here it is unstable. That means this region from here to here represents repulsion. Whereas for a distance greater than 0.8 femtometer, this region corresponds to attraction because their potential energy is negative, more stable. This is graph showing potential energy with the distance of a pair of nucleons. If the distance is greater than 10 femtometer, there will not be any nuclear force because nuclear forces are short range forces.